Unfortunately for Huygens, he was making his claim for the idea that light was a wave at around the same time that Isaac Newton was claiming that it was not. Newton had a little more pull in the scientific community, and so his viewpoint prevailed. So it wasn't until the early 1800s, when Thomas Young performed his double slit experiment, that the idea really took off. Young knew that waves interfered with each other. If you take two waves and if their crests line up, you end up with a resultant supercrest that is the sum of the two original crests. This would occur if the paths of each of the two waves differed by any integral of the original wavelengths. So say both waves had exactly the same wavelength and were emitted at the same time. This is pretty easy to see that the crests and the troughs would line up. But what would happen if one wave had twice the wavelength of the first wave? The crests would still line up and constructive interference would still occur. This is actually true for any whole number multiple of the original wave. So when the paths of two waves differ by a whole wavelength, then the waves are said to be in phase and interfere constructively. Destructive interference, on the other hand, occurs when the crest of one wave aligns with the trough of another. For complete destructive interference to occur, the paths of the waves must differ by a half of a wavelength. When this happens, then the crest of one wave lines up with the trough of another. And just like constructive interference can occur for any whole multiple of the wave, destructive interference can occur for any half integral of the wavelength. Young knew this about waves, and contrary to current theory, he believed that light was a wave as well. So he basically set out to find a way to show that light was a wave. Young noticed that if you had two sources of waves, and you stood exactly the same distance from each one, you would notice a maximum in the intensity of the waves. If you moved a little bit, you would find another area where you would detect a maximum intensity. Now we know that the maximum intensity is caused by constructive interference, so this must mean that the crests are lining up, and the waves must be a whole wavelength apart. But if you moved in between those two maximums, you would notice that the wave intensity decreased until you reached a point that you could not detect the wave at all. Total destructive interference occurs when the waves are at some multiple of half the wavelength. Young's double slit experiment sent pure wavelength light through a pair of vertical slits. When we say pure wavelength, we mean light that was all the same color, or frequency, that has been passed through a single slit. So now this light is traveling towards the double slit. If light were truly just a ray, we would expect to see two slits forming on the screen behind it. Instead, we saw a pattern of many alternating light and dark bands. We can look at how the waves interact with each other at the screen in order to produce this pattern. The dark bands occur when the crest of one wave and the trough of another meet at the screen. Notice that the waves start out in phase, but because the top wave travels a shorter distance than the bottom wave, it actually takes fewer wavelengths to get to the screen. And the difference in distances works out so that the wave arrives one half a wavelength out of phase, resulting in destructive interference in a dark area. The light bands occur when the crests of both waves meet at the screen. Again, both waves start out in phase. The difference in distances allows for both waves to arrive at the screen still in phase, resulting in constructive interference in a band of bright light. So the paths from each slit to a single point on the screen differ. To describe this mathematically, we need to define a few things. Little d represents the separation between the centers of the two slits, and we can define a single ray that comes out of the center of those slits. Young used lines perpendicular to the centers of the slits to describe the angle at which the rays leave the slits, and we refer to this as the angle theta. Since we are assuming that rays are traveling parallel to each other, we can say that the angles for both of these rays are the same. If we draw a perpendicular line from the beginning of the first ray to intersect the bottom ray, we find there is a difference in distance between the two rays, and we refer to this as delta L. This is an important distance in that it represents the additional length that the light from the bottom slit has to travel in order to become in line with the light ray from the top slit. After that point, the light rays travel the same length to reach the screen. We can define this length using a little bit of trigonometry. We drew a line perpendicular to the light rays, so we end up with a right triangle with delta L as one of the legs. The angle at the top is the same as the angle theta, and the hypotenuse is the distance between the two slits. So delta L is simply the distance between the centers of the two slits times the sine of angle theta. We said that destructive interference occurs when the path length difference is the half integer of the wavelength. So if d sine theta is equal to some half integer of the wavelength, then we will have destructive interference. We can write this in different ways, but to get rid of the zeros in our calculations, we can also say that the change in path length is equal to m plus 1/2 times the wavelength. constructive interference occurs when the path length difference is a whole integer of wavelength. So if d sine theta is equal to some whole number integer of the wavelength, then there will be constructive interference. If we go back to that interference pattern, we see again that there are alternating bright areas and dark areas. The center maximum would be a change in path length of 0 because there is no difference. So m equals 0, and we call it the central bright fringe. The bright fringe below it must be an integer of the wavelength, so since it is the next one down, it must be m equals -1. Similarly, the bright fringe above the central bright fringe must be m equals 1. If we were to continue on up, we would find m equals 2 at another bright fringe, and we can just keep going for all of the fringes that we find. In between the bright fringes are the dark fringes. Remember that destructive interference occurs at half wavelength intervals, so this particular spot is m equals -1, which gives us a -1/2 wavelength. The next dark fringe falls at m equals 0, which gives us a positive half wavelength interval. And again, we could keep going to find a half interval dark fringe between each bright fringe. Suppose you pass a light from a laser through two slits separated by 0.0100 millimeters and find the third bright line on a screen is formed at an angle of 10.95 degrees relative to the incident beam. What is the wavelength of the light? We have the angle to one of the bright fringes, so we know that represents a band of constructive interference, since it is the third band and m equals 3. So the change in path length is 3 times the wavelength, which we can substitute into our fringe equation. We are looking for wavelength, so we can rearrange and plug in our knowns to find 6.33 times 10 to the -4th millimeters. This converts into 633 nanometers, which is the wavelength of red light. This problem is actually a really good example of how interference patterns are used to determine the wavelengths of different types of electromagnetic radiation. So what is the highest order constructive interference possible for the previous system? Interference patterns do not have an infinite number of lines, and the maximum number of fringes depends on wavelength and slit separation. So solving for m, we can find a value of 15.8. And since we can only have whole number integers, the largest integer we have is 15. Now the last thing to keep in mind is that the intensity of the bright fringes will decrease as the angle theta increases. If you really think about it, this makes sense in that if you increase the angle of the light hitting the screen, it will spread out over a larger distance and decrease the intensity. If you think about the sun at noon, when the sun is overhead, the angle of light coming in is very low, so we have a very bright light. As the sun sets, the angle increases, and so the intensity of the energy decreases.